So we're going to take a look at how to find the derivative or differentiate this implicitly using our implicit differentiation. And as a quick recap, we want to recall that implicit differentiation really is just an application of the chain rule whenever we have the x's and y's all mixed together. So one of the key things that we'll recognize is that even though we are seeing y as a variable in this problem, really we want to think of this as y being a function of x. We're just not writing it as that function notation. And so now when we see something like this, for example, we can think of this function as being a function of y. And so rather than thinking of it as a function of y, we have to think of it as a function of y of x. And so what does this mean is if we were to take the derivative of something involving a y, but we want to take it with respect to x, not y, well, then this is involving taking the derivative of a composite function of an f of y of x. And as we've learned with the chain rule, that we can do that. We can take the derivative of our f, and that would just give us df dx. But because we have an inside function here, we always have to multiply by the derivative of the inside. Sorry, this would be df dy, because it would be in terms of y. But because we have this inside function in terms of x, this would be times dy dx. So our implicit differentiation basically always has where whenever we involve some other variable, usually y, then we always have to multiply by the derivative of that variable, in here y, with respect to x at the end. It's just the chain rule being used because that y is thought of as the inside. So let's apply this now to our problem that we're looking at here. So in this case, we notice that we have an implicit function here because the x's and y's are all written all together. That's what it means to be implicit versus just the y being by itself. And so let's apply our derivative with respect to x on both sides. So I'm going to take the dx on the left side. And we're going to do it on the right side as well. So one thing we know about the derivatives is if we have multiple terms on the inside, we can use that derivative and apply it almost like distribution to each of the individual terms. So I can take the derivative of the first one plus the derivative of the second one plus the derivative of the third one. And we end up still with the d dx of the 15. So now let's go through each one of these derivatives and take the derivative. So our first one is pretty straightforward, right? We're just taking the derivative straightforward wise of, and there's only an x in here, so we're going to apply our power rule. So I can multiply 3 times 10, and it gives me 30 in front. And when we subtract 1, it's going to give me x to the second. Now in this next piece, this one's a little more complicated because you'll notice that inside we actually have a product of two factors. We have the 4x to the 40th and the y as being multiplied right afterwards. So if we think of the product rule, that is where we have something of the form u times v, and we want to multiply it, or sorry, take the derivative, then our product rule says that we can do u prime v plus v prime u. So in this case right here, if I think of the first part being u, so our u is going to be 4x to the 40th, and our v is our y here, then we can apply the product rule by just finding the derivative of this first part, then times y, plus the derivative of the second one, times this 4x to the 40th. So let's do that piece next. So here, I'm going to find u prime v first. So I'm going to have 40, we're going to take the derivative of u. So this would be 40 times the 4, which is 160. X to the, when we subtract 1, we get 39. And then we have the y still here, because that's our v. So we have our u prime and our v. And then we have plus v prime of and u. So let's take the derivative of our v. So the derivative of y is just 1, right, with respect to y. But again, whenever we have a y involved in our derivative, this is where we always have to then use the chain rule and multiply by the derivative with respect to x. So it'll be times dy dx. So the rule of thumb is there's a y, then we multiply by a dy dx. And this would be times our u, which is the original 4x to the 40th. Let's do the same thing on this next piece over here. So here we're taking the derivative with respect to x of y to the 6. So we can just do the simple power rule. So if I multiply to the front, this becomes 6y, and subtracting 1 gives me to the 5th power. But again, we have the chain rule, which is what the main thing is for implicit differentiation. Since we took a derivative involving y, we have to multiply by dy dx. And then lastly, on the other side, we have d dx of 15, which is a constant. And so the derivative of a constant is always 0. So our goal now, we've gone through the process of taking the derivative. We applied this this product rule here. And so this 4x to the 40th times y actually split up into 2 separate terms because of that. And now our goal to figure out what is the derivative is just to get dy dx by itself. So let's start simplifying things and trying to get our dy dx's together in here. So what I might try to do is anything that doesn't have a dy dx, I might just move it to the other side. So I notice this term and this term don't have it, so I can subtract those. And here, if I just take 1 times the 4x to the 40th, we still end up with 4x to the 40th. And we have times the dy dx there. This other term still is a 6y to the 5th times our dy dx. And on the other side are these 2 terms that are going to move. So if I subtract them on both sides, I end up with, on the left side, negative 30x squared and minus 160x to the 39th y. So how do we get the dy dx's now by itself? Since they're both a factor of both of these, we can factor it out to the front. And I'm left with 40x to the 40th plus 6y to the 5th is equal to the other side. And then lastly, since we have dy dx times this whole thing, we can just divide, and it'll give us our dy dx by itself. So our dy dx, or our derivative, is going to be defined by this right here, negative 30x squared minus 160x to the 130 to the 39th power times y, all over 4x to the 40th plus 6y to the 5th. And this is our derivative. So our derivative is defined implicitly as well. So there's x's and y's. So if I ever need to find the rate of change at any point on this function, this implicit function, then we need to plug in both the x and y value to find that slope. Hope that makes sense.